First, I'd like to start off acknowledging the traditional owners of the lands on which I live and work, the Wurundjeri people of the Kulin Nation. But a lot of the data that I'll be talking about today has been collected all across Australia, across a variety of lands owned by different groups. I was invited by Damien to give this talk. They were looking for someone to talk about statistics being used in response to the bushfires that Australia went through in summer of 2019-2020. And he says, you get this all the time for these sorts of talks, but I will preface this that I am not a statistician by training. So let's see how we go. So the field of ecology kind of operates on a spectrum in terms of the sort of people that it attracts. So like on one side, we have what you might think of as like your stereotypical field-based ecologist who spends most of their time outside collecting data. On the other side of the spectrum, we attract people like statisticians, or it's just not exclusive to that, it could be mathematicians, physicists, or anything else, who are looking for complex and novel environments to be applying their skills to. So another way of looking at this is going from empiricists to theoreticians. So quantitative ecologists kind of fall in the middle of this. So we're ecologists who will spend time in the fields, but we'll also work with statistics. I personally don't do much in the way of field work. My PhD completion seminar was subtitled "The Abuse of Computing Resources by an Ecologist Who Does No Field Work." But I apply my skills to data sets that other people have collected for conservation purposes. So for today's talk, I'm going to consider everything to the left of quantitative ecologists on this spectrum as what we will call applied ecology, or taking stats into the real world, and everything to the right is theoretical ecology, which for me is mainly methods development. But this obviously operates on a spectrum, and there'll be people sitting at different positions. So for the first part of this talk, I'm going to talk about applied statistics in ecology. And for this, I'm going to focus on a project I'm involved with responding to the 2019-2020 megafires in Australia. So this is part of a National Environmental Science Program project via the Threatened Species Hub. In response to the bushfires, federal government put aside so much money to focus on recovery efforts. And part of that was allocated to figure out where we should be focusing our efforts to get the best results. And that's what I'm going to talk through here. So all of these pictures here are from Kangaroo Island off the coast of South Australia. So you see the picture on the left is a road through Flinders Chase National Park before and after the bushfires. So quite often on the news, you'll see lots of photos of the fires. We don't see a huge amount of what the damage is after the fact. So that's what I'm trying to highlight here. So you can see that after the fires, there's no greenery left. Some trees have survived, and we can see that these have begun to resprout in the recovery process, but there are a lot of trees that just aren't there anymore and need to regrow from seeds. So on the right, you can see that there are a lot of places in Kangaroo Island that were just completely destroyed. Places were burnt right down to the beach. Kangaroo Island also had such significant amounts of wildlife and livestock that sadly passed away, to the point that both the Australian and New Zealand military were required to show up to build mass graves. So approximately 50% of Kangaroo Island was burnt, which is about 215,000 hectares, and about 50% of the island's 50,000 strong koala population is estimated to have perished, which is especially tragic as this is one of Australia's few populations that are free from chlamydia. And then endemics like the Kangaroo Island dunner, who were already facing extinction due to threats like feral cats, have been severely affected. So as far as the bushfires across the whole country are concerned, we lost approximately 10 million hectares over a period of 7 months. So for reference, the Black Saturday bushfires in 2009, for those of us that were here for that, with only approximately 450,000 hectares. So this covered an area about 20 times as much. So estimated over 330 threatened species and 37 ecological communities that are protected under national environmental law were affected. It's estimated that we've lost approximately 3 billion mammals, birds, and reptiles directly as a result of the fire front. But this is not accounting for other taxa like insects or plants or fish. It's not accounting for indirect impacts as a result of the environmental damage. And many of these species were already in a state of decline. So after the bushfires, there was already post-fire monitoring efforts in place for some species. But these were all independent studies deployed by various state jurisdictions or private management agencies without any national or between group coordination. And that's what our project sought to address. So what was our response? So NESP was commissioned to help design a post-fire monitoring program to aid species recovery. So the part of the project I was involved with involved building species distribution models for 92 priority vertebrate species that were identified as vulnerable to the fires by the Wildlife and Threatened Species Bushfire Recovery Expert Panel. We compiled locations of existing post-fire monitoring by various agencies, and then we conducted a gap analysis via a spatial prioritization process to identify the areas where post-fire monitoring effort would be best targeted. So quickly, I'll run through what a species distribution model is, because that term would only be familiar to an ecologist. But you find that the statisticians on the call will quickly pick up what the process is here. So for data collection, this is, in most cases, just a straight observation of the species in the wild. Depending on the data set we have, we might have presence-absence data, which is binary, but quite often we only have occurrence records, things from museum or herbarium records, citizen science data at times, and these are presence only. So all we have are the ones in the data set. We have environmental covariates that we can obtain as raster stacks. We put these through various statistical modeling approaches. Depending on the data sets we have, you have different options available. Like some of these you'll be familiar with just as logistic regressions, others are decision tree based, some through maximum entropy. So there's a wide variety of options here. And then once we've fit models, we can predict back to the landscape to obtain maps of the predicted species distribution. So what are the statistical problems that we face when we're doing applied ecology? And the obvious one comes with the data. So quite often access to data is fairly restricted in ecology. A lot of these databases are maintained separately by various state-based jurisdictions. So the Victorian government has their own database, New South Wales has their own database, Queensland has their own database, so on. Various non-government organisations like BirdLife Australia have their own data sets. So getting access to these data sets sometimes is quite tricky. Not all of them are made public. Sometimes it's just a resource thing. NGOs can't afford for server hosting, but they're quite happy to send data sets to people. Otherwise, we are dealing with threatened species. For those cases, we can't actually publicize the coordinates, the species records. We don't want to risk anyone using that information for nefarious purposes. But it does mean that when these data sets are made public, we have to censor our coordinate data. So normally this just means rounding it off to the nearest latitude or longitude degree or partial degree, depending on just how threatened the species are. We can obtain the original records by dealing directly with the agencies, but you're under specific license agreements. So you'll see that for this presentation, I don't actually show you any of these records directly. Other issues we have are data quality. So we have to be concerned with like accuracy of GPS coordinates, just how old records are. So in ecology, it's like rule of thumb is you would always discard observations prior to 1970. But for other species, you might pick more recent time periods, so 1990 or 2000, if we're aware that there was some environmental change that has impacted the distribution of a species at a particular point in time. So none of these are inherently statistical problems, but what they do affect is stuff like our choice of modeling method. So like I said before, quite often the data that we do have access to is presence only, so just the ones. So the modeling options available to us are quite restricted in compared to if we had a full presence absence data set. So the data we have available can restrict the choice of algorithms that we want to use. Other things that we have to consider are the projections of our spatial data. So not everything matches every research goal. Sometimes if you're working on small areas, it doesn't really matter which projection you're using. Other cases, we really need to be specific. Like if we need everything to be equal area, like we do in spatial prioritization, we have to choose equal area projections. So other things we have to consider are model selection. So given the constraints set by the data that I've already discussed, how do we pick which modeling method is best for our approach? The research goal can affect these questions. If you have something that specifically needs a probabilistic output, you're limited to models that have that output, which requires presence absence data. Presence only based models have a relative occurrence rate output or relative likelihoods. And while some of those can be calibrated post hoc to give you a probability, it's not available to everything. Otherwise, we might choose models based on whether they let us make inference or prediction. Quite often, we might want to create a distribution map as a prediction. That's arguably the most common use of an SDM. But other times you might want to make inference. You might want to be able to plot a response curve to see what's happening for a species response to an environmental gradient. So we were limited to presence only data for most of our bushfire project. So we had to choose which presence only based method best suited us. So I've shamelessly stolen this figure from a collaborator on the project, Grisbert Valavi. This is from his PhD work comparing these different methods. So we have two evaluation metrics on the Y and X axis, which I won't really cover here. The important thing is that you want to be closer to the top right-hand corner for better performance. So we were coming down to options where we had maxent, maxnet, ensemble models, downsampled random forest. But you can see a lot of these methods are all very similar up the top. So our final choice ended up being maxnet, just from a software implementation perspective. But when we're working with presence only data, we also have to account for things like sampling bias. So when we go out into the fields and we're collecting data, more often than not, we're doing it in areas that are accessible. So especially with like museum and herbarium records, you'll find a bias towards roads or towns where people already are or have ease of access to. So you can see in this figure here, with the heat map that's plotted underneath the occurrence points, that there are definite hotspots where this happens. So presence only methods require background points, which you can think of as a pseudo absence, or that's not a correct definition. But we have to simulate zeros essentially. And these methods were comparing the environmental conditions in areas where we do find the species compared to the background sample. So we can look at the difference in the environmental niche the species is found in versus where it could potentially be found in. So there are different ways of approaching this. Like a default method is just random backgrounds. So you just take your background points from wherever. Target group background is using the presence records of other species that have been observed that would be observed with a similar sampling bias. So generally this is within taxa. All birds would be sampled the same way, but they'd be sampled different from mammals. So you wouldn't use mammals for background data here. Other options are various ways of constructing a bias layer. So these could be kernel density estimates. They could be using rasters that have been generated as like an access layer. So in terms of travel time from the nearest town of X population. So all of these are different things that we have to consider when we're creating the models. So we've done this for the bushfire project. I'm just going to focus on some species from Kangaroo Island because it's a nice visualization. So this is a map of Kangaroo Islands. Everything and that little hashed out area on the left is what got burnt. And most of this area was burnt at what they consider a high severity class. So Kangaroo Island was hit quite strongly. So we probably have about half a dozen species on Kangaroo Island that we were considering in this project. I'm only going to highlight two here. So on the left, we have the Kangaroo Island short-beaked echidna, and on the right, Kangaroo Island glossy black cockatoo. So down the bottom, we have their relative occurrence predictions. So yellow
David, sorry, we can't hear you. We've lost sound. No, still can't. David? I think he might have lost internet connection. So maybe if we could just give a few minutes to maybe get David to reconnect. No, we can't. We can't hear you, David. Would you like to try calling in as a phone? And maybe, so somehow the audio is not working, although your screen was sharing okay. Oh no, it's back, it's back.
It's back?
Yeah.
Okay. Do you need me to go back slides?
Yeah, it actually about a few minutes ago.
Mm-hmm. Yeah. All right, slides are back?
Yeah, I think maybe one slide before, yeah. So from the start of,
Start of this one?
Yep.
All right, sorry about that, I'm not sure what happened. Yeah, so the two species I'm going to focus on for this part of the talk. So the Kangaroo Island short-beaked echidna on the left, and the Kangaroo Island glossy black cockatoo on the right. So they have predictions of their relative occurrence rates in the two maps down the bottom left. So high relative occurrence rates show up in yellow, low as in purple through blue, and these maps have been cropped to just the areas that got burnt for the purpose of the project, but we do have these predictions across everything. So the main thing that I want you to take out of this is that both of these species, there are areas of high relative occurrence that have been identified in the bushfire affected area. And that's problematic for the ongoing persistence of these species. And so we've put this through a spatial prioritization process. I'm not going to run through this figure. I'm just going to point out that the stuff on the left has been done, the stuff in the box on the right is currently in progress. But what we do is we combine the predictions for all of these species with the known post-fire monitoring locations, so we can mask those out of the prioritization process because they're already included. And then we use a tool called zonation, which essentially ranks areas based on how useful they are for our monitoring program. So for outputs, we'll get something like this. We've variously done this for taxa on their own or everything together, because there's a variety of research goals as part of this project. So to interpret these figures, the higher the number, the more important it is that we do post-fire monitoring in those areas. So you can see that for birds and mammals is actually quite high all across the range of what got burnt. But you can see that it's much more important for mammals to be monitored in Eastern Victoria or Southern New South Wales than we have for birds. And you can also see that for mammals, we actually have areas that show up over in WA, don't for the birds. And this is just related to the fact that we didn't have any WA-based birds that were listed as threatened from the bushfires. So one of the things I was asked to talk about is what it's like working with government for statistics or non-government organisations and the problems that come with that. So I've already talked about things like data access and how hard it is to get things sometimes, but we've also got data formats. Different groups will use different date formats, or they'll have things measured in different units. Different coordinate systems, and all those things need to be considered. Quite often, there's also a lot of issue with heat dragging, which is very problematic on time-sensitive projects, like responding to a bushfire. It actually takes quite a bit of time for the government to turn around and actually supply you with the data. Otherwise, research goals quite often conflicting between governments and research bodies, so those need to be settled. And arguably the most annoying thing as a researcher is that you send everything off to the government and they always come back with, oh, but how about this little tweak? Once people start to see the results, they start to get a bit more invested in the project, which we would have preferred earlier in the piece, but that's when they start coming back with, hey, let's tweak this parameter to do this, let's consider this extra species, and a lot of that sort of work builds up. But working with government and NGOs does come with benefits, one of which is data access. Field data is expensive to collect, so being able to get access to data sets that are already existing rather than every researcher having to go and do it again themselves is beneficial. We also get to see our results put into practice. The government has used our prioritization to start allocating millions of dollars in post-fire monitoring funds to various organizations so that we can start working on our actual response to the bushfires. But we also get to see our results put into practice for extra things. Once people start to see the results out there, they get to use them for a variety of projects that weren't in the original brief. So example for this is that as part of the spatial prioritization, which is the goal output for the project, we had to build SDMs for each individual species. But those outputs are now really useful to various different groups. BirdLife Australia is currently using our bird-based models for some of their own monitoring programs. As well, the government wants to allocate funds across all taxa in certain things. Different groups, once they're starting to design their own monitoring programs, only want to consider the species or taxa groups that they're actively involved in. So BirdLife Australia doesn't do any monitoring for reptiles, so they don't want to consider that in their own, setting up their own research. So for the second half of this talk, I'm going to talk about theoretical statistics. So this involves my PhD work on joint species distribution models, or JSDMs. So I introduced the single species model for the bushfire project. But joint species distribution models are a relatively new approach for modeling multiple species simultaneously while accounting for residual associations. So this could be species interactions or shared environmental responses, dispersal limits, and things like that. So this is a really important development, but most of the work gets done here is by either statisticians or people who slant very heavily towards statistics on that scale I used in the earlier slides, which is great from a model development perspective, but when we want to see the uptake of these methods in the wider ecological community, they can become quite difficult. I don't expect anyone to read all of this. I'll highlight some key bits in a second. This is a paragraph from a paper by William Lowery back in 1959, pleading for the increased use of mathematical notation in ecological literature. So the cases he makes, so substantial saving in premium page space, which I think is fantastic that he thinks this is the first option that should be listed. It is important and it does make it more concise in terms of getting a point across. It allows for a more precise communication of logical thought. It is much easier for someone else to read your equation than it is whatever sentences you've constructed to try and describe what you're doing. And this one's I find really impressive considering we're going back 6 decades. But calling for the increased assurance of reproducibility of methods and results by applying the techniques of others, which is really important considering we're currently dealing with a reproducibility crisis. And finally, the increased speed and precision in translating your approaches to other languages, which I think is very important in this day and age when international collaborations are much more prominent than they used to be, especially with a lot of other countries that don't traditionally publish in English language. But this also comes with the caveat that these advantages accrue in proportion to the care used by the author in the use of notation. So just by using equations doesn't actually give you any improvement. You need to use them carefully. But yet, 6 decades later, we're still in a position like this. Most ecologists don't like equations. I think it comes down to the way most of us have been trained. I definitely didn't do any statistics throughout my undergrad. So it makes it much harder for a lot of these methods to see significant uptake. So the reason we have that is that these ecologists will be faced with something like this. So they look at these 2 different things. They look completely different, but this is the exact same model from 2 different places described in 2 different notations. So while this might be interpretable to a statistician, even if they have to read the paper to get to that point, this is a really big barrier to most ecologists. So the problem we have with this, they use different symbols for the same parts of the equation. They use the same symbols for things that are completely different. And then to add to the confusion, once again, it's the same thing with a different symbol. And then my personal favorite one is that a latent variable is not a latent factor except when it is. So these are all problems to do with the communication of this to ecologists. So to start my PhD, I came from a zoology background, but I decided if I was going to do a PhD, I was going to jump into the deep end. I was going to learn stats, and if I was going to do that, I may as well go right in. So I had this issue trying to figure out what all of these different proposed JSDMs were actually doing, how one differed from the other beyond each author's claim that theirs was the best. So my first chapter was taking all of these different approaches, putting them into a singular framework with consistent notation, and then being able to identify the differences in the models. So I get a core model like this. I'm only going to quickly run through it. So the first line is latent variable. So a species is present if the latent variable falls above 0, absent otherwise. The shape of this latent variable's distribution is similar to how we would interpret a regression equation. So mu here is our linear predictor. So we have our measured variables and our regression coefficients. It's a multivariate model, so we have a correlated residual error, which is where we identify our species residual associations. But by giving everything a core model to be based off, we can start to identify what models are doing differently. Some of them are just slight variations. So this one here is just adding a hierarchical step to the regression coefficients, which has both ecological and computational benefits. But some of them will actually differ far more drastically. So the model on the left estimates a full rank correlation matrix, and that scales poorly with increasing numbers of species. So the one on the right takes a latent factor approach in an attempt to solve this curse of dimensionality. So what we can see now is that we have two linear predictors here. So mu is the same one that we have in the model on the left. So this is explaining our species response to our measured environmental variables. And then our second linear predictor is done through a factor analysis. And we can think of this as a species hypothetical response to unmeasured environmental variables. And this is where this dimension reduction comes in, because instead of estimating a full rank correlation matrix, we can use these latent factors to return a low rank approximation. Instead, this model also takes a further step using a Dirichlet process to further shrink that factor loading matrix by making the assumption that similar species are going to respond in a similar way to these unmeasured variables. And because of this, we now have an uncorrelated residual error. So by using a singular notation, it's easier for what I just refer to as like a lay ecologist to interpret what these models are actually doing.
So I think we've lost David again. Might just need to see if he returns. Okay. So I don't know sometimes if it's just me or, but thanks Adele, that gives confirmation that it's not me. Hopefully he returns soon. So while we're waiting for David to reconnect, please feel free to ask questions like in the chat as we go along, or like put up your hand, and we'll have a combined one at the very end.
Can you hear me now?
Yeah. Welcome back, David.
Thank you. I had to sign in on my phone. So I made the decision to stay late at uni and present from here because it was going to be tight making it home from my last meeting to my home internet. But the university's internet has apparently died.
That's very surprising.
I'm in the middle of setting up tethering so that I can continue. How long have you lost me for? Because that's really hard for me to tell.
It hasn't been that long. So if you show the slide, I can tell you where we were.
David, it was exactly when you said that by making these assumptions, you've got the uncorrelated variance for errors.
Okay, so I haven't lost much. As soon as I get tethering set up, I should be able to share screen again. Well, while this potentially takes a bit of time, I'm happy to start answering questions now about what I've covered rather than holding everything to the end and making everyone sit here in an uncomfortable silence.
Dave, I might ask a question. In your earlier work, when you are doing the distribution map to go into the ranking process, is the uncertainty like a factor there? I think this place might have this many birds, whatever, but it's actually very uncertain. I could be really wrong. Is that kind of uncertainty fed into the ranking process?
Are you referring to the uncertainty in the predictions?
Correct, yes.
Yeah, so we definitely do look at the uncertainty in our predictions. At the moment, the way zonation is set up, we're just using our best prediction, if you will. There are other processes to look at the uncertainty in your predictions. A lot of those are far more complex to set up. So because we have such a time-sensitive response for something like bushfires, we elect to proceed with something where we weren't looking at that uncertainty. But zonation does have some inbuilt uncertainty as part of its calculation. So that is looking, that's at least partially accounting for it, but it's not accounting for everything we could if we had the time to set up something that's explicitly including the full range of uncertainty in the predictions.
Thank you, Dave. I'll follow up if I may. The ranking process, I know you showed a graph, I didn't really sort of read too much of that. Is that just, is that like a mathematical ranking thing or just like the experts talking?
So the ranking is done mathematically by zonation. That's not part of the process I'm involved in. So I won't get this 100% correct. But it's looking at ranking the sites within a single species. So for species A, like these are the most important ones, these ones are less important. It does that for each species individually, and then it's doing something to combine all of those things to come up with a prioritization accounting for all of the species preferences. So this can account for external inputs from experts. So in our case, all species are treated equally because that's our part of our research goal. But we could, for example, weight mammals twice as highly as reptiles if that was the research goal. So there are different ways of running the prioritization based on different simulation parameters.
Thank you.
I do see some questions popping up in the, I see the chat pop-up window, but then I can't access the full chat on the phone. So if someone else wants to read those out.
Yep, I'm happy to do so if you're willing to take the question now.
Yep.
So Terry's asked a question, what packages in R do you use to fit the model on the right? So that would have been the latent variable model.
So with this for the JSDMs, yeah. So the model on the right is from a package called GJAM, which is GJAM. So it's a generalized joint additive model from memory. So it comes from James Clark over in the US.
Is there a particular advantage of that particular package, or this is just something that you're more familiar with and that's why you're using it?
So that is a package built so that came with the paper where this model was first presented.
Mm-hmm.
Yeah, generalized joint attribute modeling. That's the one.
Mm-hmm.
So you would be able to build models like this using JAGS or STAN or various other Bayesian programs. But GJAM has been built by James Clark and his collaborators specific to this. From memory, they have their own custom-built MCMC sampler that runs through C++ because it makes certain parts of the process quicker.
are you okay taking more questions, or did you, you're still setting up the slides?
Yeah, it's taking a while to set up the hotspot, so I'm happy to keep answering questions as we go.
Okay, I wanted to actually ask a few things, which I thought you might actually cover later, so I was going to hold it off, but so I might be stealing a bit of your thunder later.
Yep,
which was that it's about the data collection, because you actually mentioned that so there's a sense that ecologists collect data sometimes out of like convenience, and so naturally there's a bit of a bias in that data. I'm wondering if there's like, do you take into account that bias somehow in the model?
So we don't account for the bias in the model explicitly. When we're using a presence background model, so like something like MaxNet, MaxNets, what we do is that we generate our background sample points with similar bias, or as close as possible to the same sampling bias as the actual occurrence records. Because otherwise, if you have your background samples showing up in areas that the species isn't present in, just for reasons that like the species never got there, it's or completely different environmental conditions, the model can get your estimates wrong purely because of sampling bias.
In terms of actually, thanks for that, the data collection, actually, so is it only ecologists collecting the data, or you know how there's sometimes these citizen science projects, and then people can report like whether they've seen a particular species or not at particular areas. Mm-hmm. Like, is that ever incorporated in your work at all, or it's always much more better curated one coming from ecologists?
So we definitely do make use of citizen science data. It does depend on the species. For a variety of reasons, citizen science tend to focus more on your traditional charismatic species. So like you'll find like most people might decide to go out and look for koalas more so than various insects, for example, because they're not as interesting to the general public. So most state databases won't include citizen science because it's the stuff they've collected themselves. NGOs will quite often have a lot of citizen science data. BirdLife Australia does. Quite a few fungi-based data sets, citizen science-based. Although in those cases, the citizen is quite often a researcher or a professor who works in the field anyway. So we do make use of that quite heavily. So a project that I'm not talking about today is looking at roadkill risk of herpetophiles on roads in Taiwan. And that's using an entirely citizen science-based data set.
Very interesting. If anyone else has also questions, feel free to put in the chat or also put up your hand so I can just, you can unmute yourself in that case.
Sam here, I've got a question. If I can, yeah, cool. David, you mentioned earlier that in ecology courses, you did an entire ecology course without doing stats. Is that something that's changed now?
So this is actually one of those times where this is something I was going to talk about later. Yeah, so this is actually the very last slide I have before my acknowledgements. So right at the end, I'm going to have a section where I talk about the things that we can be doing better to help the uptake with these things. The final thing I get at is that we should be teaching ecology students statistics. I come from a zoology background. So I did my bachelor's in zoology here at University of Melbourne. Throughout that entire course, I reckon I did 1 chi-square and 2 t-test calculations. None of which I did myself. We were given R scripts. We were told, change your file path. And then you just do Control A, Control Enter, run everything. We're not going to tell you what's happening. And most we got some help with interpreting what values are. It does change once you start hitting postgrad. So there are, there's a subject at University of Melbourne called Thinking and Reasoning with Data. So that was probably my first proper stats anything. And then you do get little bits of it in postgrad ecology subjects. Those tend to be run more by quantitative ecologists, or at least here at the University of Melbourne, or at least the topics considered are more in the quantitative realm rather than your traditional behavior-based sort of stuff that you get in undergrad. Yeah, but it is definitely changing. There are subjects that are showing up at the University of Melbourne now that are specifically statistics it's for biology students, so it's analysis of biological data, but it's run joint between the maths and stats departments and bioscience by an ecologist.
Yeah.
This is the sort of stuff that I think is super important going forward. Like you can see, like some of the equations that I've had to learn for my PhD weren't even remotely in the realm of possibility when I did my undergrad. Like, never knew they existed. I did reasonably well in math at high school, but the moment you hit the undergrad, never had to deal with equations again, and you just lose it. So it's yeah, it is improving. I think we can do better, but it's also not something that I expect fixes overnight.
Okay, thanks.
So it's quite a jump to go from doing t-tests to latent variable models. That's I did statistics undergrad, and I can tell you I didn't do latent variable models.
So I did have a master's degree in between my undergrad and the PhD. It was also in quantitative ecology, and I worked on occupancy models, so like logistic regression based. So I didn't go a complete jump from a t-test that I didn't understand straight to a latent variable model, but it was a big jump going from master's to PhD, because I went from having to understand an equation that was widely used and widely described to something that is not really used by many ecologists because it's new.
Mm-hmm. So there's actually a couple of comments that I saw I'll relay to you. So Ben's mentioned the fact that it's better to learn no statistics than bad statistics.
Oh, yeah, 100% agree.
Yes. And I'm kind of glad that even if you only learn like something along the t-test, you still did a programming language. So I actually think at least that.
Oh no, I was given an R script, told how to open it, to highlight everything and run it. I was not taught programming during my undergrad either. That's something also that needs to fix. Like I can't talk for other disciplines, but ecology and quantitative ecology especially, there is a huge shift towards programming heavy sort of questions that students are facing. Yeah, it's definitely not taught early enough, I think, for most students to get the full benefit out of it until they're able to like hit a PhD and sit there for a few years and get used to it.
Mm. So you reckon like still people, it'll benefit from learning programming, not just statistics, because there's also statistical software where it's not so much programming, right? Because you can click and
like SPSS or Stata, like the GUI based. Like I think those are useful as like a first step. But as we discussed at the start, I'm currently involved like in the Replicats project, assessing like the reproducibility of science. And I think one of the biggest hurdles to that is just like computational reproducibility. Like I can take someone's R scripts, rerun it, and assuming it's set up properly, I'll get the same results. I could follow someone's instructions for the buttons they clicked in a GUI-based program, and there's no guarantee I hit them all in the right order, that I hit every tick box that I'm supposed to and get the same thing.
So Terry had a point where she said it would be good to have applied statisticians who speak ecology. And I think that's a really good point where, you know, some people know that maybe the mathematics behind the statistics, but maybe when it comes to like the domain knowledge, like you need to be able to speak with the people who have the domain knowledge and translate the statistics into there. And did you want to share your experience around that, David?
Yep. So no, I agree. So there are actually pushes in various camps these days that labs, or if labs are too small, things at like a school or a faculty level should have embedded statisticians in various groups. It's like the University of Melbourne does have like a stats consulting centre that people can go to. But ideally what we have is like you have a statistician embedded in a research group or like partially embedded across several within a school. And then by being based in a group, whether it's ecology or psychology, chemistry, or whatever it is, they're able to start picking up the domain knowledge by working with these people directly. And then they're, you know, conversely, these labs are able to start picking up the statistical skills.
So I'm just a bit mindful about the time. So I'm taking we might not be able to get your slides up. Do you think you could provide us a bit of the rest of the content summary?
Yep. So most of what I had left, I was just going to show a couple of scary equations and highlight what it is we can do to make interpreting those easier to ecologists. And honestly, the biggest thing is that a lot of these things can be represented visually. So for prediction, which was the slide that I last got to on my screen, but I don't think got through to you guys. So now that we're in the multivariate space of JSDMs, we're now doing prediction in a multivariate space. So by doing that, we build these big multivariate normal distributions model, but our predictions of different community assemblages, we have to calculate them with integrals. And these are big nasty equations that are going to send ecologists running for the hills. But what we can do is we can represent those visually. So like in the two-dimensional case, because that's the easiest to visualize, you have a y-axis and you have an x-axis, you have a species on each. And then you have essentially a top-down look at the probability distribution between the two species, you know, how they're co-occurring, which species is more likely to occur, things like that. Like if you show that to an ecologist and you highlight that the box in the top right corner where the latent variable for both species is greater than 0, this is where both species are present, that's interpretable. But a latent variable formula isn't as much. So I think I'm about to get back in. Let's see.
You can maybe show us that visualization you're talking about.
I think I'm back. All right, back in the meeting. I potentially need to be made co-host again to share screen. If I didn't keep it already.
I've got to get Damien actually. Damien, could you make?
Yeah. Done.
Okay, thanks.
Done. Screen. All right, is the slides back? Yeah, can everyone see the slides again?
Yeah, I can see it.
Perfect. I will just mute the phone so I'm not in class. so let's slip right ahead. I've shown you the wrong presentation. 1 second. Yeah. All right, I'm back to the right presentation. So let's okay, there should be no more echo. So skip ahead. Cool. All right. So which slide do you see? Because when my preview does not show the slide that I'm on.
We're still on the first slide.
First slide. Okay. Let's try again.
So it could be the delay in the internet connection. So if you maybe stop your video, that might help things.
Yeah, I'll do that. All right, do you see a equation now?
Yeah, can.
Perfect. Cool. All right. So I'm not going to talk through this equation. This is just something most of you statisticians will be familiar with, just the right probability of two things occurring. There we go. So for an ecologist, this should be much easier to interpret visually. So you put your two species on the different axes, and then the latent variable interpretation is that when the value for a species is above 0, it's present. So where this is above 0 for both species up here, both species are present, both absent down here, and then one or the other in the top left and bottom right diagonals. What's useful about this approach is that you can also show to the ecologist that there is still a marginal distribution for each of these species. So you can still consider them independently of each other, depending on what you're doing. Yeah, but if you want to calculate the probabilities in this distribution, you get some nasty integrals, especially once you start adding multiple species. But if you showed that equation to an ecologist and then showed them this figure and then said, you want to calculate the area of the probability distribution that falls in this quadrant, they'll understand what it's trying to do. So they'll be able to say, they'll be, look at this and say that you've got probability of 0.16 of both species occurring at a site, 0.31 of both species absence, and things like that. The visualization also aids the fact that we can condition these predictions. So we might have additional knowledge from another study so that at the site we're considering, we know that species A is present. Right. So essentially we can truncate this multivariate normal distribution such that it's always going to be greater than 0 for species A. And then because the probabilities always have to sum to 1, we end up with updated probabilities. So now an ecologist will be able to look at this and say they've now got a probability of 0.23 of both species occurring by conditioning their prediction on additional knowledge that we have from extra studies. So this is really useful for us if we have a particularly wide spreads or well-studied species. So like something like cane toads, for example, that there's always studies on because we're trying to get rid of them. We do have quite a lot of knowledge about where they are, and we can use that to aid our predictions of other species. So what I'm going to do now, the bit to end on is the, so what can we be doing better section. So I've already showed how shared notation and visualization can make things easier, but I'm going to quickly go through some suggestions from a paper by Edwards and Orgamethe from 2019. So some guidance on using mathematical notation in ecology. So this might seem really obvious, but we don't see this in ecology, and that's define all of the terms. Ideally, this is in a table exactly like what we see on the right-hand side of the screen, but you'll be surprised just how frequently something won't get defined. People just assume because they're talking about a model that's widely used in ecology, they can just talk about a handful of the things rather than everything. But for someone who's coming in, doesn't have a history in that particular type of modeling method, unless they can find the source paper that people start referring to and bringing out partial equations, this is actually a real hindrance. So other things is like italics, boldface, capitalization, other things to aid reading in the equation. Things like equations always default to italics, especially if you're using them in a sentence. You identify your vectors in boldface. These aren't going to be things that's super common in ecology because, like I said, we don't get taught stats, so we don't learn this notation, but it makes things easier for us to interpret things. Using subscripts appropriately. So like keep these indices representing different values of quantity. So for us, this is frequently site or species that we're iterating things across. The other thing that throws off ecologists in my experience is when people don't use dot notation. So like when you're including all indices in a particular direction, instead of pulling out a particular one and you're referring to everything, quite a few papers will just use the index for the dimension that is being subset. So if I wanted to refer to a species across every site that I've predicted to, and I use just the site index, most people will read that and get confused that a dimension has disappeared in an equation. Whereas if this was done as I comma dot, it becomes clear that the whole dimension is being retained rather than being subset. Superscripts, something that can be really confusing. Ideally, these get reserved for things like powers or representing the transpose of a vector or a matrix. I've seen far too many papers that mix indices between sub and superscripts just to make it easier to read. Like they think I and J next to each other as a subscript. It's too hard to see them on the screen or whatever reason they want to use, and they use I as a subscript and J as a superscript, and things get confusing, especially when they start mixing them with models where they're raising things to a power. Distinguishing variables from parameters, so some things in lowercase, uppercase, Greek letters, things like that. Being able to group things in an equation will generally make it easier to identify, like, these are the bits being controlled by the ecologist with their input data. These are the bits that are the estimated parameters that you're using as outputs. These sorts of groupings make that stuff much easier. Like avoiding multi-letter names, like everything should be a single letter. Like if I read a paper and the equation has AB, I don't know if that's supposed to be AB as one thing or if that's A times B. And this happens quite often in ecology where people try and use variable names to try and make the equation human readable. Your regression might be, species response is indicated by temperature plus environment, elevation plus, whatever other variables you want. But when you write full sentences, they don't fit on the page, so they quite often get shortened. So when things become temp plus elev, they become really hard to interpret unless the equations are adequately defined in text as well. But that kind of defeats the purpose. Using equations and not just code is a big one in ecology. Quite often new methods will be proposed and what they put in the text is JAGS code or something for a new Bayes model rather than the actual equations. So you find quite a few ecologists who are happy to work with some of these models, will be familiar with the JAGS code because that's how they interact with it, but they wouldn't be able to interpret the equations if you put them in front of them. So abide by conventions that are already in place, but still define everything. It's like, as you've seen, like I went through 7 different methods that were all defined using different sets of notation. Like, I realized there are existing multiple conventions of ways to write things, but like within a like subfield or a particular topic, ideally you keep to convention. I mean, otherwise, other certain conventions aren't like an overall syntax approach. For ecologists, I and J, generally represents species or sites, and people will be able to know what corresponds to what. If someone else came around with a paper and switched this to A and B, leads to confusion. Otherwise, what I find really useful is revising your notation early on. So when we went and put all of our models into a shared framework so that we could identify how these models are differing, what we did is once we'd come up with a shared notation, we brought in other ecologists in the lab who weren't invested in this project to see how they'd interpret things. Like, we didn't want it to be a case of, I know what this means because I've spent the last 6 months staring at a whiteboard trying to come up with a set of notation that works. But the moment anyone that's not myself or my supervisors looks at it, it doesn't make any sense. So revising your notation, not only early on, but by dealing with people outside of the project is really valuable in my experience. Like I said, my last slide is when you need to teach ecology students statistics, I realized there is already a lot to teach students from like a conceptual level in ecology. Things like predator-prey interaction and game theory and various other things. But most research projects are hitting the point now where students need a statistical background or some familiarity with programming for them to be able to hit the ground running in the limited timeframes that master's or PhD research projects present. Because the more time people have to waste learning these skills at the start of a project, the less they get out of the research project itself and what they get to do with the result. Like, if everyone has to spend the first 12 months of a 2-year master's degree learning how to read an equation or load their data set in R, they're not going to get as much out of it as someone from a statistics background who decides they want to start applying themselves to ecology. And then I'm going to end on my acknowledgement slide, which is various collaborators across the 2 projects, all of the places that I shamelessly borrowed pictures from last minute when I was putting this together today, and then the various groups that I'm associated with. And then that's me done.